we're looking at the Viterbi algorithm for trying to compute the most probable sequence of hidden states for a given sequence of x's, a given sequence of observed states. And we wrote down this quantity. We defined this mu k zk as a quantity that we were going to try to find a recursion for. And so we just used some Markov properties here. We factored the distribution, and then we moved the max in, and that was very nice. And now we have this recursion. So let's write it down. Let's write down what we got. So we got mu k of zk equals the max over zk. Make a little room here. Zk minus 1. Probability of xk given zk times the probability of zk given zk minus 1, the transition probability, times mu k minus 1 of zk minus 1. And let's think about for what k's does this hold. So this is looking very nice, right? We have this nice sort of recursion here for these mu's. And let's think about, so for what k's does this hold? So when k is 1, then this is z0, so that's kind of a little bit strange. So but for all other k's greater than 1, this is fine. So let's restrict this to k from 2 to n. And then let's think about what mu1 should be. So mu1 of zk, or of z1, well, what is that? Mu1 of z1, it's the max over z from 1 to 0. So this is just an empty maximization. This is just a trivial maximization. So this is just the probability of z1 and x1. So if you wanted to check, you could also say, okay, what's mu2? Mu2 is the max over z1 of the probability of z1 to 2 and x1 to 2. And if you followed this same factorization through here, then you would have, what would it be? It would be probability of x2 given z2 times the probability of z2 given z1 times the probability of z1 and x1. And this max would, there would be no max inside here. We just have the max over well, it would just be the max over z1 outside. So mu1 of z1 is just the probability of z1 and x1, which we can factorize as the probability of z1 times the probability of x1 given z1. And this is known. This is just the initial distribution, and this is just the emission probability. So this is all known, and these are known, and we now have a recursion that we can use to compute mu, starting from mu1, and then doing mu2, mu3, mu4, so you go in order, so it's sort of in the forward direction, all the way up to mu n. And then once you have mu n, what is mu n? Mu n is the max. So let's figure out. So mu n, what does this give us? Mu n is the max. Let's write it down here. Mu n at the last step, mu n of zn is the max over z from 1 to n minus 1 of the probability of the whole thing, x from 1 to n, z from 1 to n. Right? Because k equals n. And now, in order to get the maximizer over the whole thing, we just take one more max out here, max over zn, or at least to get the maximum over the whole thing. And then we get, that's just the maximum. So once we have mu n, then we can get the total maximizing value easily. Okay, so that's great. So we got the maximizing value, but wait, we wanted the maximizing sequence. We wanted Z. We wanted the argmax, not just the maximum value. So how are we going to get the argmax? Well, it turns out that to get the argmax, you can follow essentially the same procedure. So if you were to write down this algorithm, implement it in a computer code, and at each step you keep track of the maximizing sequence, then for the next step you will be able to compute the maximizing sequence up to k minus 1. Then for the kth step, you will be able to compute the maximizing sequence up to k. So let me illustrate. Maybe I'll illustrate briefly how that happens. So if we have, this is like, if these are the possible values of z here, maybe it just takes like 3 possible values. And this is step 1, 2, 3, 4, 5, etc. up to n. Then, we want to find the maximizing, or maybe it just goes up to 5 or something like that. Say it just goes up to 5. Oh, no, we'll think about the general thing. So we want to find the maximizing sequence over all of the n, the whole path. And so if we start out, we have 3. Let's do it sort of by induction. So let's say we have the maximizing path up to step 4 here for each possible. So what we want to keep track of is the maximizing path that terminates at this, let's call this maybe A, B, and C, that terminates at state A for the hidden variable z. So this is going to be, so this is saying that, like, if it were here, that would mean that z4 equals A. Okay, so maybe the maximizing path that ends at z4 equals A is, I don't know, maybe it's something like this. I don't know. And then maybe so then we also we're going to assume that we have the maximizing path for z4 equals B. And maybe that's, I don't know, maybe it's something like this. Something like that. And then let's say that we also have the maximizing path for z4 equals C. And this is the maximizer over the joint distribution from 1 to 4 of the z's and the x's. So in other words, it's the thing, it's this thing. It's the path that gets this value, that gets the value mu for z4. It's maximizing over the z's that came before z4. And let's say the path for this one is, I don't know, maybe it's something like this. Something like that. Now, so, we're going sort of by induction. We assume that we have these paths, and we want to find the path that maximizes that for a given z5. So for z5 equals, let's make this, I don't know, we'll make it a different color. We'll make it red. So now we want to find the path up to 5 that is maximal for z5 equals A. So how are we going to do that? Can we reuse this, all this hard work that we did to figure out these best paths? Well, this path, it has to go through one of these. It has to have some z4, the best path. And what these equations are saying is that the path which maximizes, so the path which has this quantity here, is that we only have to check each of these. We only have to take, we only have to take into account the additional sort of probability of this step from 4 to 5. That's this part here. And, the emission at 5. And from there, we know that the maximizer, a maximizing path for all of, that ends at z5 equals a, can be obtained by using one of the maximizing paths that ended at some zk minus 1. That's what this is saying. This is saying that a maximizing path that ends at z5 can be obtained by appending, that ends at, z5 equals a, can be obtained by appending a to one of the maximizing sequences that ended at one of the zk, at the z4s. So in other words, it's saying that we only have to check one, these three possibilities. Either append it to this guy, to the yellow sequence, try that, see what you get, compute the value, try that, compute the value, and try that, compute the value, and take the maximizer over those. You're taking the maximizer over the value of z4, and that one of those three is going to give you a maximizer up to z5 that ends at z5 equals a. Okay, so I hope that was clear. I wanted to just sort of explain it in words rather than write down the formal algorithm, because I think it's good to get the intuition for what this recursion is doing. But you can, of course, you can write down an algorithm to implement what I described in words here. And then, so once you can do that for, of course, z5 equals a, you do the same thing for the others, b and c. So you would do that also for, these others here. And then you've made the full induction step, and then you're at 5 and you're ready to go on. You have an optimal path that ends at each possible value of z5. And once you do that, you get all the way to n, and you're done. All right, so that's the Viterbi algorithm. That's how it works, and that's how you compute the maximum probability path for a hidden Markov model. So this illustrates, this is a great illustration of dynamic programming, and sort of, at a more broad level, the basic idea of what was going on here is that the problem of finding a maximal path decomposes into these sub problems. That's really the key thing, is that it decomposes into these sub problems, and you only have to sort of condition on the value that it ends at here, and then you can break it apart into the sub problem. So okay, so that was I hope that was a clear explanation of how this works, but it's a very, very important sort of concept to get your head wrapped around what's going on with this dynamic programming, because it's very useful in a lot of different contexts. And I think this is a great example of dynamic programming to sort of cut your teeth on, to get your head wrapped around what's going on, at least for in an optimization type of scenario. So this is for an dynamic programming for an optimization type of scenario, and the forward-backward algorithm is for a computing probabilities and inference type of scenario.